Just public business.
Hello, everyone. Welcome everyone back to the afternoon section. Firstly, we're going to start with Shadi, and luckily we have you here, and he will introduce himself and start the talk. Thank you.
Yeah, thank you very much for having me here. Indeed.
Let's make sure people can hear us.
Oh yeah, I think that was muted. Just double check. No, that was.
Can people online hear us? Especially Shadi.
Could you hear us?
There might be no one online, to be honest.
No, there are a few people there.
Check real quick.
Yes, we can hear you. Thank you very much for asking.
Thank you, Christian. All right.
This is Shadi Albarqouni. Indeed, I do have a slide for the introduction. I will just probably move on to the slide. So I'm originally coming from Gaza, Palestine. I did my bachelor, master's degree in electrical engineering. Then I worked there for a couple of governmental institutes. Then I got the DID scholarship, one of the prestigious scholarships from Germany, where I indeed moved to Bonn, Germany, started my PhD, working cutting edge technologies for electron microscopic data, but mainly with image processing, like image reconstruction, denoising, etc. Since I'm coming from family with medical backgrounds, and my dad and my siblings, all physicians, and I worked at the hospital at some point for a couple of years there. So it was just quite passionate to go work with native language. So this is where I moved to Munich, to the Professor Nasir Nabab chair, computer-aided medical procedure, where I spent there, did my PhD there, and spent a couple of years as a postdoc team lead, worked with brilliant students coming from different countries, different backgrounds, working even in industry. So it was just a great time that I spent with those guys. Afterwards, I got this nearly prime fellowship, where I spent 1 year at Zurich, and I can be at College London. Then I got this group leader position at the Helmholtz Institute with 1.8 million euros funding for 5 years. I still have this group, but recently I just moved to the University of Bonn, University Hospital Bonn, as a professor there for computational imaging research. So indeed, I do have labs in Munich and Bonn, with a couple of PhD postdocs and some radiologists, medical research assistants. Still, we have also 2 positions opening that we're going to open soon. These are a few photos from Bonn. So Bonn is the exploding city, right? Well, Germany is well known for beer. The very cool place is also there. There are so many kinds of breads there, right? Every single state they have their own type of breads. So many castles, and of course, wonderful lakes and close to the Alps, right? I do have a question for you. I wrote 2 presents for you guys. The question is, what is the castle that you see it here? What is the name of this castle? So I do have some options. Oh, probably need to go to the slide to answer the question. Can you please just log quickly to the slide? I didn't have pointed this earlier enough. Sorry. There's a code, maybe you have seen it, this guy. Can you just log into the slide.com and enter the code? So you could just run this further. It's very cool. So 280-8443. So could you raise your hand if you're done? Already? This is from the bio, you see here, this is the data posted. This is from the October Fest. This is how the traditional indeed, clothing, etc. We do have also lady, so whatever I think with that. But since we're you're done, right? I mean, we just go to the text, right? I'll just skip that. Probably get the numbers, right? And then
It says what enclosed.
let me just reopen it if you don't mind. We'll just waste them some time. Sorry, Nasir, yeah? Let me just check. But do you have a name? Someone knows like the name of this castle?
I just guess.
You guess, okay.
You have someone who knows.
Yeah.
You need to do an image search on Google.
No, please don't.
Oh, you've been there. Correct? Oh. Look.
Probably now they got the answer, no? Join the quiz. Oh, so there are a couple of people probably addressed the quiz, no? Guys, did you answer the quiz? So what are the names that we see it here? Those your names?
Yes.
Yes?
Yeah.
Do you see, like, if you join now, do you see the quiz questions or not yet? Not really.
No, it's still get ready.
Keep active. Hopefully we haven't seen the answer. Guys, can you see now that? Otherwise, it's okay, it's fine. Do you have a name for the castle? Where is located? Yeah.
Bavaria?
Bavaria. We need another another person, but we can do another. Okay.
Okay, good.
What's the name?
No chance. No chance.
Yeah. But did you Google it? No.
No, I did.
You have been that. So which one? Sorry.
Oh, okay. I don't know.
What about? So there's a lady. Yeah.
Okay.
Great. Well, we might have like probably question later on. So there's still one present though. Okay, let's move on.
100% associated, he's been there.
Yeah. So let's move on. So this is indeed what shaped our research profile in the past few years. No, sure not. I mean, what we are working on is like three main research themes: computational image research, federated learning, and affordable AI technology. I mean, I don't want to go through all this, but this is like when you work with limited amount of data, there's self-supervised and supervised learning. This is what we work with our clinical partner that you see in the top right. The logo of the partners like the clinic, Uniclinic unit. But when you bring more data, then you might have the domain gap, right? Domain shift. So you probably need to work either in domain adaptation or image translation techniques, right? This is what stuff that we have to work on with our partners of Bosch, Samtec, Philips, etc. We also worked on generalization, but not the domain generalization, they're like the class generalization, like how you could make a model generalized to unseen classes, that kind of what we've seen before. So we indeed work with machine learning, future learning, with our colleagues and basic reality set. But we haven't been only working on imaging, so we have been working also in incorporating the sparring knowledge for some electronic health data, right? So there's a series of work that we work on geometric deep learning, graph computation at first, together with our partners at Helmholtz Munich. But this is like more the classical approach. So you keep working on that until you reach the desired performance, right? But what we have been working on also recently is try to make the models interpretable, explainable. So we touch up on topics like robust optimization, uncertainty quantifications, outer distribution section, and also fairness, how to make the model with age, gender, etc. Although this is might be like debatable, if we talk about political domain. But what I have been essentially working on, focusing on, is indeed the federated learning. And this is what I would just probably talk about. This would be the main topic of our talk today. How many of you have read this book by James Surtees? The Wisdom of Crowds. Okay, so indeed he brought like a couple interesting examples, real world examples like from the CIA and others. The main message that he did was trying to communicate: crowds are smarter than individuals, no matter how brilliant they are. Yeah. He had few conditions though to make this collective intelligence happen. We're gonna go through those guys, I mean, later on, like at the end of the slides, at the end of the presentation. So the outline for today's talk, I will probably just go to the general introduction to federated learning and touch on our paper that I published in Nature Machine Intelligence last year. I think we could skip this, like the challenge in the clinical workflow. You probably know that we have shortage of the number of radiologists, even workload, which indeed causes a lot of error discrepancies. And what makes things even worse, do we have radiologists here? No, right? So what makes things worse is indeed like the intra and inter-observability among the radiologists, right? So that's why we need this AI algorithm. However, we have, I mean, a lot of challenged limitation though, right? Pretty cool paper pointed out those kind of challenge perspectives, etc. I mean, this is like one of the nice papers that indeed outline the progress that's happening with all the challenge and opportunities. What we're going to talk about today is mainly focused on the data limitation and the model trust, right? I believe. Yeah, so this is indeed where we talk about the domain generalization, right? This would be part of the model trust. So I'll just first make this, well, maybe set the stage by defining the domain generalization federated learning. So the domain generalization, the goal that you must have heard this a couple of times this morning, how to train learner model from one or several databases, right? And make it generalizable to unseen domain. And here are a few examples from computer vision or from physiology databases. When it comes to the federated learning, as indeed, well, we could formulate a problem as given like C clients, like imagine here, those green boxes are hospitals, and they have their own data, this NC data point. So the main objective is to train classify or segmentation, whatever model, leveraging those distributed data points in a privacy preserved fashion, which means the data shouldn't leave the hospital, shouldn't leave the green boxes here. And the way to do it, well, there's a pretty cool work from McCann et al., who came up with this federated average algorithm. It's pretty simple into the way it works. You initiate like model parameters in these yellow boxes, you pass it to the green boxes to the different hospitals. They are trained on their parameter, on their data. So these parameters that will transmit it to them were trained on their own data. Then they send it back to the yellow boxes. Then all these weights are averaged basically, right? There must be some like an average based on the number of data points you see here over the total number of points. It's quite different from the distributed learning though, to things like communication efficient, and the data here are not identically distributed. The question I have for you, well, maybe you could skip that question. I'm not quite sure. Do we really need federated learning? What's your thought here? Because I think in the next few slides, I'm trying to convince you that we definitely need it. Could you just add this question if you don't mind? If you don't mind, just so oh yeah, very cool. Yeah, pretty cool. So maybe you could skip the next few slides. I mean, the slide will have limitations for the right learning, right? Some works that have shown, I mean, that including more data, even don't see everything in data, yeah, not cleanly annotated data, would improve the model performance in a logarithmic fashion. Yeah. However, this is not straightforward in particular medical domain. A few works have, I mean, you must have seen that. Well, indeed, like if you do have access to the face recognition databases along with the MR or the CT, you could basically just retrieve all the data and probably reconstruct the faces of the patients. That's why there are a lot of regulations came, like the GDPR, HIPAA in the US, and the recommendation that, well, recommend using federated learning. The question that I do have for you next, and I think I promise you this is the last question. What the challenge do you foresee in federated learning? I think this is the last question. Do you get the whole concept of how federated learning works, right? And probably won't be needed, I mean, when integration. The question is now, what about the challenge that you might phase if you want to deploy or implement federated learning. Okay, very cool. Now, I think we stop here because that goes beyond the story down. Yeah, well, it's about the standardization. So indeed, like I have done this a couple of times, and indeed, like most of the answers that I have, standardization, data heterogeneity. I mean, most of that need, like the answer was just about the data heterogeneity, which is indeed like a big problem, right? Apart from the legal, political, probably the communication, privacy issues. And indeed, it's a problem that we have seen it in the couple of publications paper, right? So you can see here from this paper, where if you do have non-IID, so non-identical independent distributed data, the performance drop from this blue curve, I'm looking at the CFR10, from 90% or over 80% to like half, like 40%, right? When you do have non-IID distribution. So the data heterogeneity, for like having clients with a few classes would indeed deteriorate the performance of your model. So this data heterogeneity problem is indeed a serious problem, right? And there are a couple of solutions, like the Fedprox, the average momentum, BIR, etc. So I'm not going through this kind of, well, the math, etc. There are also other, proposals like to work with a data sharing strategy. So we do share part of the data, like have central data that we share in the institutes. But still, it's about the privacy concerns that the clients might have. There's also pretty cool work about CLPN, the rationalization, where they share only, like for example, for the CLPN, they only share not the patronalization parameter, like not the statistical parameter, over only the renormalization parameter. So this is what they do indeed, and it seems to be working to some extent. FitBN says, well, no share, so you don't share the patronalization parameter at all. Notice that it's neither the static nor the renormalization parameter. Seems to be working on at least 4 examples. Well, it's quite challenging when it comes to the medical domain. And this is where I need just talk about the whole recent work. So, of course, data heterogeneity just mentioned, like it's quite challenging. It comes from different factors like intra-standard variability, demography, multimodal data, and the noise either in the annotation or the measurements, right? So I'll need to just touch up on our recent work that we had published in Nature Machine Intelligence. So the idea behind this work is to do unsupervised anomaly detection and bring them on. We train them all on different databases, healthy brain MR, and try to detect anomalies on so many different pathology databases coming from different institutes. Those institutes are not from the same institute that we train the model on, basically. The idea is pretty simple, right? I mean, we based it on our previous work that we published in mid-IA and RSNA. It's just computational encoder. Unit shape, so you train it on healthy data, and with whatever like particle loss function, could be L2, could be perceptual loss, etc. And then during the testing, all the inputs, you pass, for example, an image or train data with pathology. So the model wouldn't be able to reconstruct this pathology. So what they would do basically is just generate a pseudo-healthy version of that patient. Then what you could do is just simple arithmetic operation like subtraction, then hopefully get the tumor for the pathology. So this is what we show in the RSNA data. So this you see here on the right-hand side, like on the top row, you see the MR data. On the middle, you see the annotation by the radiologist. And the last row, you see the pathologist coming from these anomaly detection algorithms. So this is basically nothing to do with the rate learning. This is the work that we published a few years ago. We show like in more quantitative measures how this anomaly detection works much better than the simple pre-shielding that is used in the clinical practice. Yeah. But surprisingly, it works even better than the supervised model with transfer learning. Yeah, you can see the numbers here. For example, you can see the 17% F score with the unsupervised. It's quite close to the 20 F score coming from the unit. And there are also similar numbers here for other pathologies, right? So that indeed just motivated us to see how that works on federated learning, data coming from different institutes. Why this is why this might be challenging? Well, if you came across this data, this is coming from our colleague at Munich. They were showing like this is the same patient scan, different time points, different scanners, Siemens, Philips, GE. This is the same patient. Then they try to threshold to see the quantify the multiple sclerosis. On the right-hand side, you see the figure where they either plot the quantity, like the volume of the lesions. What you see here, look, I don't see. Oh, sorry, give me a second. I think this is the pointer, right? Yes. So what you see here, there's like if the patient like scanned by whatever that Siemens scanner, it will be 5 milliliter volume. The next day, if he scanned by GE, it will be just double volume, right? So you just look at these numbers, how indeed, well, the volume would be drastically changed, either drop or just decrease by just changing the scanner, right? By the way, the threshold was optimized by the radiologist to make it like more or less similar. So this is bringing us to the challenge that we do, how we deal with this kind of heterogeneity. Different scanners, different appearance, right, of the brain imaging, how we can train the model on these different appearances. Now we don't see it even in the federated learning because there's privacy preserved fashion, so we don't see the data. So what we had in mind, well, what about just try to disentangle the representation of our brain and body to do a presentation. One capture the shape, the anatomy, and the other one capture the appearance, how the coloring basically, let's call it. And we only share the appearance the appearance parameter among the institutes. This is the anatomy because they share the same anatomy, this brain anatomy, right? For healthy patients, we should share the same behavior. But the appearance or the coloring or the styling, this is locally, this is for the institute itself, because we might have different standards, whether Siemens, GE, etc. So this is what we try to do. And to enforce this, we try to have a specific loss function. So this is FPL-LOL. I don't recall what that is indeed. So the SCL, I think, shape consistency loss. So basically what we did, try to change the shape, maybe with gamma shift or whatever, like different appearance. Then tell the model this representation should be quite close, similar to each other. So we only focus on the shape, or indeed just try to to make them like share the same representation. So they are agnostic to the appearance, right? So this is the first loss function. The second one, LOL. I need to remember what that is. Orthogonal loss, latent orthogonal loss, indeed. So what does that mean? We try to make the representation of the shape and appearance orthogonal to each other. Yeah, this is our hypothesis. Yeah, that this shape and appearance, they shouldn't really correlate. They should be orthogonal to each other. So we try to enforce this in our loss function. And just to push them away somehow, right? So they don't carry any information, or there's no leakage from the anatomy to the shape. So we trained this model 1,500 scans, like volumes, and we tested. So these are healthy data coming from those databases, and we tried to test it on six databases coming from like MS lesions, glioma, etc. Right? Here's the latent space. You can see how indeed what was nicely done. So, for example, those are 4 patient different databases, right? And if you look at their shape, so they're close to each other because they look similar, right? But if you look, this is their shape representation, right? If you look at their appearance representation, they will be just clustered differently, right? Because this is how we train the model basically. So of course that will look like that, right? We enforce that with the objective function. Now let's have a look at the results, because this is what is indeed important. So what you see here, few brain imaging from the bottom to top, I think the quite good to the most difficult cases, average somewhere in between. And what you see here, those are the ground truth, lesion segmentation, and the pinkish is the false negative, and the white are the true positive. And those are different algorithms. So the first one is the local, second is the rate average, and CLOPN, we talked about it, fit this, so this is our approach, and the last one is the data centralized. But what you see here is the zoom version of those lesions, right? And of course, the more whitish is the better, right? And you can see like here that like our method was doing a pretty good job in most of the cases, right? Well, might be also doing bad in some other cases. Maybe here there's some false positive, etc. But indeed, even better than the data centralized model. And you might have discussion we could argue later on how that happened, right? What you can see also on the right, on the left-hand side or left-hand side, you can see, I mean, the performance across the lesion size in millimeters square, and what you could observe here, most of the model just fail when the lesion is just pretty small, right? So that's just what should be done there. Yeah. Probably there are these numbers like the underscore probably, or the area in the curve. I would probably skip that. Or comparison of unsupervised and supervised models. I think we could just move on. And maybe you could also skip that. I mean, this is like some analysis we did just to see if there is any bias towards age, gender, etc. We haven't observed any kind of bias. So this is also a pretty good indicator of how the model will generalize well to unseen data coming from different standards, different sites. And we haven't observed any bias like to certain age or gender, etc. There are other works also we have done in this direction. There's like Fifth Barrel, the second one here that was published at Melba. This is about skin lesion, but mainly for semi-supervised learning. So we presume here, our assumption there are some clients that we have no annotation at all. Some other clients have partially annotated data, etc. How we could just bring them to the same scale, etc. We also brought the idea of peer learning or like peer coaching, yeah. So let the clients just they are similar to each other, let them just learn from each other the distribution, the parameters, etc. So we try to cluster those clients based on some sort of similarities. The last one is the fifth norm. Is the federated learning with modality-based normalization, where we try to indeed train models to do liver segmentation from different modalities like MR, CT. Once again, the assumption here there are some clients have only MR, some others have CTs, others have combination of MR, CT, and how we make the model generalize to these different modalities like modality agnostic, and also generalize to those different sites. We tested also on unseen sites as well, and it was working very well to some extent. You see here the results on the first row, how the liver segmentation looked like on CT and MR compared to other methods. I'm almost done. Yeah, so I think we just, there's a lot of work that we need to do for federated learning. I just wanted them here, those in orange. Yeah, there are also similar works, and not mine though, but super interesting. So, and CLOPN once again, there's also interesting work that was published, I think, the CBR from Chile. And we indeed, like, together with my colleagues, we were on board with this editorial board of the IEEE TMI special issue on federated learning, but we had also very cool papers on federated learning. I truly believe there are a couple of them on the generalization as well. Essentially, we published also this work at Neuros. It's benchmarking federated learning, also like on a couple of databases, medical databases, along with a couple of institutes like UP and NWA, UC Berkeley, ABM Development. Now when it comes to the slide, right? So remember, he set few conditions, James, right, to make this collective intelligence feasible. Can you guess what are the conditions? So the crowds are smarter than individuals, no matter how brilliant they are. But there are some conditions to make this happen. Any guess?
Generally knowledgeable.
Yeah, yeah. Heterogeneous, true. I mean, there should be some diversity, right? And they're similar to each other, then what's the point, right? It doesn't make any sense. So indeed, so the first one is diversity. Every single client or like hospital, they should come with their private local knowledge, etc., right? Their experiences, and you could just, well, do the analogy here, demographics, scanning devices, cohort selection, and so on. The other one should be independent folks, right? I mean, it should be independent, right? If you come with your supervisor, well, what's the point? I mean, you have there, right? So this is like it's extremely important as well. There's also interesting stuff, but that may be more to the maybe the CIA example that you brought. But indeed, it works also here, and I can relate to this when we talk about this shape or this appearance parameter that we need to keep it locally. So we call it tacit knowledge. So this is something that we need to keep locally, like similar to the appearance that we have in our paper. Nevertheless, all these great things, but without coordination and aggregation, well, won't work, right? So this is really extremely important to have proper aggregation and coordination. And I believe if you did have those kind of conditions, then the federated learning would hopefully work. Yeah. Great. I think if you have a question, I think there should be some questions that are relevant. But if not, I do have spare slides, like I do have extra slides. So just let me know if you still have time to tell something.
Short of time, allow for the audience to give one question for the speaker.
Yeah, great.
I have a question.
Please.
So I feel that diversity is kind of a recurring theme across all the presentations. We want our data to be diverse, or sometimes we want our models to be diverse. People who suggest we should use ensembles. Is there some exhaustive list of the traits for which we like? How do we define diversity? Is there an exhaustive list of traits that we might be looking for?
Yeah, this is a very interesting question. Yeah, I mean, that could go on like different, well, axes, right? You just mentioned, I mean, this morning we listened also to your talk, like you talk about different sides, different, like even annotators, right? I mean, they come with their experience, right? So, I mean, it's quite hard to tell, like, because you need to cover all those kind of factors, right? Annotators, different size, different devising, like machine, right? Could be, well, I think it's the most thing that I think was mentioned this morning.
Let me make the scope of the question a little smaller. Is there any exhaustive list in terms of scanner variations in radiology that we might be looking for?
Well, not quite sure. I mean, not quite sure. I mean, and when we talk about MR, for example, I mean, so we have seen that there is both variation, right? Variability within the MR itself. So there's intra variability within the scanner, right? If we talk about CT or X-ray, it's less pronounced, right? So you don't see it much. But still, I mean, there's little differences that you need probably to work on the patient side. Exhaustive list, not quite sure, I'm not really aware of that. But you know, the community, probably the sphere is also like involved. There's like I think we call it future AI. If you Google it, there is like 3-4 papers just submitted to the Lancet, and I think it's already on archive. Now we work on standards for how we call guidelines, how to make the models, etc. And we had maybe some sort of kind of exhaustive list. So maybe it's worth looking at this. Yeah, but I don't recall indeed what we there are a few factors, but you probably could look at that. Yeah.
Thank you for the